We begin with Hurricane Milton this morning. Milton is rapidly intensifying, threatening to become one of the most devastating storms in recent history.
Extreme weather like hurricanes and typhoons are getting stronger, and they're intensifying faster and more frequently than ever before.
The rapid intensification this morning has been mind-blowing.
Storms we thought would hit our coasts at a Category 1 are exploding overnight into massive hurricanes, causing billions of dollars of damage.
Got the 10 a.m. numbers here on Hurricane Milton, and it continues to be terrible news.
For decades, weather satellites have given us a view of these storms as they form at sea, travel across oceans, and make landfall, hitting our cities and coastlines. But as storms intensify more rapidly, our satellites just aren't giving us enough data to understand this new phenomenon. Just last summer, Hurricane Milton shocked meteorologists.
And a major hurricane is barreling toward Florida. Hurricane Milton is now a powerful Category 5.
Jumping from a tropical storm to a massive Category 5 in under 48 hours.
We have seen an increase in the center winds, almost 100 miles per hour in just 24 hours. It has just exploded in those incredibly warm ocean temperatures.
With stronger storms and more people living on the coasts, we can't risk letting storms develop into monsters when nobody's watching. That's why researchers at MIT Lincoln Laboratory have been working on the next generation of weather satellites. Satellites that can take us inside a hurricane almost 10 times more frequently than current satellites, so we can predict rapid intensification of a storm before it's too late. The world's first weather satellite was launched by NASA on April 1, 1960, from Cape Canaveral, Florida. TIROS, or Television Infrared Observation Satellite, gave us the first blurry photos of our atmosphere from above. TIROS revolutionized the way we understand clouds and the atmosphere, and it changed the way we forecast weather forever. TIROS was a polar orbiter, meaning it looped over the North and South poles. Polar orbiters fly about 520 miles above the surface, and because they pass over the poles every day, they give us a great view of the polar regions. But they only take occasional snapshots of the rest of the world, because their orbit changes every day as the Earth rotates underneath them. In 1966, NASA launched the next big class of satellite, a geostationary satellite called ATS-1. Geostationary satellites sync with the rotation of the Earth, so they always hover over the same spot. They're great for watching one area on Earth continuously, but they're way further out in space than other satellites, over 22,000 miles above the Earth's surface. Each of these types of satellites are equipped with a wide array of sensors that detect various wavelengths of light from the atmosphere. Each wavelength band shows us different things about weather. Infrared sensors, like the one on TIROS, are great for sensing atmospheric temperature, while the visual band shows us the shape of clouds and the color of the Earth's surface. But to see inside a storm and understand why our hurricanes are changing faster than ever, researchers use microwave sounders. Unlike visual and infrared light, microwaves can pass through clouds unaffected, which means that satellites can scan through the broad clouds of a hurricane and see its internal structure. The problem is we're not getting frequent enough microwave scans to predict or even understand rapid intensification.
Many of the most memorable and damaging hurricanes are also remembered for how fast they gain strength.
We've seen some really eye-popping examples of rapid intensification in the last few years.
Rapid intensification
occurs when a storm's maximum sustained wind speed increases by at least 30 knots in 24 hours, a phenomenon that's becoming more common and making storms more destructive. From 1980 to 2023, 177 land-falling Atlantic tropical cyclones hit this threshold, and the 5 most economically costly hurricanes since 1980 all experienced rapid intensification. Because these hurricanes escalate so rapidly, traditional satellites can miss key parts of the action. Our current suite of microwave sounders only give us a view of developing hurricanes about every 6 hours. In a rapidly intensifying storm, a lot can happen in 6 hours. A convenient way to solve this problem would be to put a microwave sounder on a geostationary satellite, so we could get a continuous view of an area of interest, say the Atlantic Basin where hurricanes form. But geostationary satellites are really far away, and the further away you are from Earth, the larger your antenna needs to be in order to get a clear picture. Large antennas are both expensive and tricky to design because they have to be folded up during launch and then unfold once in space. We could also launch more polar orbiters, but they're not cheap either. They can cost billions of dollars and take years to develop and launch. They also take days to revisit the same area, so we'd need a lot more polar orbiters to really change how often we scan hurricanes. What if, instead of one giant satellite always watching, or one more medium satellite taking a look every few days, we flew a constellation of tiny satellites that continually passed over the area of interest? Since these tiny satellites can fly close to the Earth's surface, they can have a small antenna and still get great resolution. With several small satellites working together, they can revisit frequently. That's what Lincoln Laboratory fellow Bill Blackwell and his team have been working on for the last 10 years, and it's called the TROPICS mission.
The idea of TROPICS was one where we wanted to try to make a better measurement, better characterizations of tropical cyclones, the environment surrounding the storm, and that's best done in the microwave wavelength range. The microwave wavelengths can penetrate clouds, so you can get a sense of the temperature and the moisture structure in the atmosphere around the storm, even in the presence of clouds. So the idea with TROPICS was to essentially proliferate a constellation of those sensors. We have many more observations, much more rapid observations, so we can start to capture how the storms are changing and how they evolve and try to improve the forecast.
To fly a constellation, they had to figure out how to make the satellites cheaper. And the best way to make a space launch cheaper is to reduce size and weight. Meaning before Blackwell and his team could launch, they had to figure out how to fit the scientific instruments that are usually on a satellite the size of a car onto a tiny satellite the size of a loaf of bread.
So there's an antenna, there's a receiver front end, there's all the electronics that run the payload, the back-end processing, all that has to be miniaturized.
To miniaturize these parts, they looked to other rapidly shrinking technology. Smartphones.
Your iPhone has a lot of the integrated circuits that we need to make the radiometer payload. So we use a lot of those commercial components that are, small, highly integrated, very low power consumption, and we use those in the radiometer. One of the challenges of using these commercial parts is they were not made to fly in space.
Your iPhone might survive a drop from your pocket, but these components needed to survive the harsh conditions of launch and spaceflight.
So we had to qualify them for use in spaceflight. So that involves a lot of testing, vibration testing, thermal testing, radiation testing, a lot of analysis to make sure that they can withstand the rigors of launch and operating in a space environment.
Once they got the technology working in the lab, they flew test satellites to prove the technology could work in space. The Lincoln Laboratory team worked with new space companies to build and fly their missions. The bus, or the body of each satellite, was built and supplied by Blue Canyon, and the launches were flown by Rocket Lab. In the years since, 3 pairs of TROPICS satellites launched, with 4 satellites successfully orbiting us right now. In 2024, when Tropical Storm Milton was developing in the Gulf of Mexico, TROPICS captured its rapid intensification from tropical storm to Category 5 hurricane in under 48 hours. TROPICS is revolutionary in how frequently it lets us see inside storms, and the team designed it so forecasters could use the data right away. Levi Cohen at the Joint Typhoon Warning Center tracks storms in the Indo-Pacific, where we have even less data available than we have in the Atlantic Basin.
We rely almost entirely on satellite data. That's why microwave images are so important, because it's basically our only good tool for getting down underneath the storm's cloud tops and seeing the structures that can be associated with rapid intensification.
The Joint Typhoon Warning Center provides hurricane and typhoon forecasts for the United States Department of Defense in the Northwest Pacific, South Pacific, and Indian Oceans. To protect military infrastructure and personnel from hurricanes, the Joint Typhoon Warning Center needs as much data as they can get, as often as they can get it.
The military uses a lot of equipment that can be very sensitive to extreme weather conditions. It's very expensive equipment, so you need to be able to move it out of harm's way. So in terms of saving money and avoiding disaster, having that lead time is really important. Rapid intensification threatens that lead time because you might think that only a weak storm is coming in a couple of days, and then all of a sudden the storm explodes. One of the biggest problems with rapid intensification is that although computer models are getting better at forecasting it, they can only do that well if they have a really good picture of what the storm looks like currently. But the problem with the current constellation is that we're not able to get successive images over tropical cyclones more than once every 6 hours. And that's problematic because if we don't have images more frequent than that, it's really tough to piece together the evolution of the storm.
Data from TROPICS allows the Joint Typhoon Warning Center to see inside typhoons when they otherwise might be waiting hours for new data.
We're treating it operationally as an experimental product. We have it in our systems. We're able to look at the data and we are leveraging it alongside other data. It is helping in the sense that it's supplementing those temporal gaps. Sometimes we're waiting hours and hours for an image. So getting one from TROPICS where we otherwise would have had none can be very helpful, and we have benefited from that.
While the TROPICS project has given the U.S. unparalleled views into hurricanes, the concept of a constellation of microwave sounders is useful around the globe. One company is taking that idea and running with it.
Yeah, TROPICS set out with, I think, a bit more targeted goal, measuring the tropics, kind of that latitude band. Our goal is global.
That's John Springman, head of space and sensing at Tomorrow.io, a company that provides hyperlocal forecasts for the entire globe, giving everyone from individuals to companies and governments the best possible weather forecasts to prepare for storms, maximize agricultural yields, and mitigate risk from severe weather. To get the data they need for their hyperlocal forecasts, Tomorrow.io is launching their own constellation of satellites based on the TROPICS program.
Our overall goal is to fundamentally improve weather forecasts, and that'll improve our downstream products like our weather intelligence. So microwave sounders are really complementary to the Ka-band radars that we're launching. You can kind of use them synergistically to improve forecasts of precipitation specifically, which is one of our key interests. We landed on MIT Lincoln Lab and specifically the TROPICS technology, and using that as a starting point for our mission.
According to Tomorrow.io, the global revisit rate for microwave sounders is between 2 and 5 hours. And once the scan happens, it takes another hour for that data to reach forecasters. Tomorrow.io wants to bring the revisit rate to under an hour and the lag time down to just 15 minutes.
Satellites that we built, we're getting our constellation of microwave sounders up now. We're able to do it because it's much more cost affordable. It allows us really to finally get more granular in our ability to forecast all the different areas in the world. We'll tell Uber when it's going to rain or when they're going to have an increase in demand for any city around the world. So they'll know to have enough drivers on the platform ahead of time so they don't have things like surge pricing or ETAs. And we do something similar to that for every single industry. So how do we help railroads not get derailed? How do we help airlines run more on time?
This data will not only improve existing weather forecasts, but also provide forecasts for places where there aren't enough data to make good predictions. In many parts of the world, local precipitation forecasts are made using only ground-based radar. But ground-based radar installations can only see a storm about 100 miles away, and installations are few in developing countries. For Tomorrow.io, the goal is to close these gaps with space-based observations. For the 2025 hurricane season, NOAA's Commercial Data Program contracted Tomorrow.io to provide their satellite data to better track developing hurricanes, helping our country predict and prepare for destructive storms before they hit our coastlines. Weather affects all of our lives. Whether you're evacuating before a storm or just wondering if you need that umbrella, better, faster forecasts save money and lives around the world. In the future, when hurricanes rapidly intensify, we will be better prepared to prevent the worst. All thanks to tiny satellites developed right here at MIT Lincoln Laboratory.